And good morning, good afternoon, good evening, everyone, and welcome to CG or Data webinar. This is the very first webinar of the year in 2022, and it's a great pleasure to have James Day speaking with us. So James came from his early higher education in the geology research career from Durham University, England. Then he traveled westward, passing the Atlantic Ocean, and working as a postdoctoral researcher at the University of Tennessee and then the University of Maryland. Before he started his position at the Scripps Institution of Oceanography more than 10 years, slightly more than 10 years ago, 11 years ago. And Jim has working on mantle geochemistry, cross geochemistry as well as cosmochemistry. And he's made many contributions in different directions. And one of the unique contribution has been made on first pointing out the highly sidereal elements concentration of the low abundance on the lunar samples. Actually, it's relevant to the talk I'm going to give today. So I do like to quote one of the phrase in James' website, which I liked very much, describing the time they were collecting meteorites, staying in the tent in the Antarctica. So he says that the time in the tent is not time on the ice, searching the stones that keep signs of light. So with that, I will give the rest time to James to present his work, and we will leave about 10 to 15 minutes to discuss with our audience later after your presentation. So with that, James, please.
Thank you very much, Johnny. I hope you can all hear me. Johnny, just put your hand up if you can hear me. Perfect. So thank you so much for the invitation to talk to you all. I know some of you and others I don't. And my name is James. And as Johnny nicely introduced me, I don't need to introduce myself. Today, I'm going to talk about something slightly different from what I've been working on the moon to date. And that's looking at the implications of impact melt compositions for a late heavy bombardment cataclysm to the moon. I'm just going to move my slide forward here. So hopefully you've seen the slide move forward. This is sort of the outline of the talk that I'm going to give. It's essentially looking at the compositions of impactites and the late heavy bombardment. And so first I'll talk about what the late heavy bombardment is, otherwise known sometimes as the terminal cataclysm. I'm then going to outline three issues that we have that we're aware of. The first is the age of the impactites. And when I say impactite, I'm referring to a melt rock or breccia. And I'm going to show you some examples of these in thin section and also in hand specimen. The second issue is the impactor compositions using highly siderophile elements. And I'll explain why those are useful and important. And then the third issue are the compositions of the ejectors themselves, so the lithological variations that exist in and on the moon. And then once I've gone through those issues, I'm going to introduce a slew of new data from the Apollo 14 and the Apollo 16 landing sites, and hopefully outline to you why a combined approach to this problem might be useful for understanding the likely sources of ejecta and the evidence for a late heavy bombardment. And I'm showing you images of the lunar surface as I'm going through this talk. These are just generic images, either of the Apollo 14 or the Apollo 16 site and various craters that exist therein. So many of you are probably familiar with the idea that the moon may have been struck by a series of large impactors about 3.9 billion years ago. This is the idea of a terminal cataclysm or late heavy bombardment. It was originally proposed by Bill Hartmann in about 1966, and this is the original drawing on the right-hand side. So what this shows is time on the x-axis and temperature and cratering rate on the y. And what he suggested is that there was an intense bombardment at some period. He didn't know that period back in 1966, but we now think it's around 3.9 billion years, after which many of the crater floors were flooded with mare basalts. And Chunga 5, of course, has sampled some of those basaltic rocks. The origin of this paradigm has come about in several ways. The most important of which is actually crater counting, looking at the lunar surface, counting the number of craters, looking at the relationship of those craters to one another, and inferring ages for some of those craters. This is very important. Once you have a crater with a well-known age, then you have a tie point in the crater counting chronology that enables you then to relatively date the lunar surface. And this crater counting has also been applied widely to other bodies that have significant numbers of craters upon them. In fact, it's been applied to bodies that don't have a lot of craters on them, specifically Venus. Now, obviously in 1966, Bill Hartmann didn't have any of this crater chronology calibrated. He didn't have ages, precise ages. But the return of samples from the moon by the Apollo samples and also by the Soviet lunar samples provided dates that could then be calibrated to this crater counting chronology. And some very important work in 1970s by Food Terra and others, including Granville Turner, where they used argon-argon dating, were able to specifically and precisely date many of these impactites, giving calibrations to this crater counting chronology. And based on that, they inferred that this cataclysm at 3.9 billion years had indeed occurred. Lunar cataclysm, terminal cataclysm, or late heavy bombardment paradigm has evolved through time, and it falls into several different categories. So the first is that the late heavy bombardment was dominated by Imbrium formation event. Now, of course, Chunga 5 landed to the west of Imbrium, and so it would have been affected by Imbrium, at least the material underneath the landing site. And the idea is shown here in this image from Wilhelm's work. He's done a lot of cartography of the moon, and you can just showing you a very different image, but this is the near side of the moon. And you can see that Imbrium ejecta really dominates the near side of the moon. And that, of course, is because it's one of the youngest large impactors. The other ideas have been that it's a moon-wide phenomena, that the late heavy bombardment really did occur and it pummeled the lunar surface, not just the near side and the far side. And Imbrium was just the last of these very closely related events. And so everything we see on the lunar surface is late heavy bombardment material. And then finally, there's the extreme end member, which is actually that the late heavy bombardment never occurred at all, and that it's just simply a function of declining rate and preservation of impacts. And one way of looking at and thinking about this is to look at the impact rate on the diagram shown on the right here versus the time before present. So this is the beginning of the solar system at 4.568 billion years or so ago. And this is going up to about 3.5 billion years. And you can see that there's these various ideas. So one idea is that there was an exponential decay in impact rate. That's essentially the number of impactors that were available in the inner solar system to strike the inner planets decreased as a function of time. Another idea is that you had a sawtooth cataclysm, the idea that you might have had a at some stage in the past, possibly 3.9 billion years ago, something in the outer solar system affected asteroids and other impactors in such a way that they began to move and infall towards the sun much more significantly. and some of those impactors struck the Earth and the Moon. One of the ideas that has come from the late heavy bombardment is the Nice model, the idea that Jupiter and Saturn tacked inward in the solar system, driving material towards the inner solar system and creating the terminal cataclysm or late heavy bombardment. This is all wrapped up. This paradigm is all wrapped up in a series of more and more complex ideas. And as I mentioned, the first issue is that it all comes down to the initial idea of crater counting. So once again, you can take a map of a surface of a body that has lots of craters, and you can work out, okay, this crater came first, this crater came second, this is the oldest crater, and so on. And there are many people who are experts at crater counting. I'm certainly not one of them. And one of those people is this gentleman, Robbins, who in 2014 pointed out that the crater counting chronology is not that well calibrated. On this diagram here, you can see age in billions of years before present versus lunar counting chronology. And what he shows is that there are a series of craters for which we think we have good ages. There's a series of locations for which we think we have good ages on the Moon. Chunga 5 is not shown on here, but it would be somewhere around here. It's an important tie point. What he points out is that we're missing a large swath of time. Maybe Chunga 5 is filling in that time to some extent, but it's very regional. We only have a regional picture of the Moon. So, for example, most of the Apollo missions landed in the equatorial sort of belt of the Moon. So we don't have a really good feel for what was happening at higher latitudes or lower latitudes. And we have no idea what the rate of bombardment looked like before about 4 billion years ago, because everything that we've dated from the lunar surface that we think is from an impact event tends to be younger than 3.9 billion years. So the calibration is very poorly constrained, especially between 3 and 1 billion years. It's arguably not constrained at all after 4 billion years. And the uncertainties on the calibration can be as big as 1 billion years. A good example of this is just this table here that shows that different large basins like Oriental, Imbrium, Crisium, Nectaris, Serenitatis, and so on, depending on how you do the crater counting, for example, Serenitatis could actually be younger or older than Crisium based on our current knowledge. This is also compounded by the fact that our knowledge of age dating is quite poor for the Moon. This paper by Bernke and Harrison came out in about 5 years ago, makes the point that argon-argon age spectra are seriously affected by the monotonically declining impact flux that occurs on the Moon. And the consequence of this is that you tend to get a lot of ages at around 3.9 billion as a consequence of the way in which these argon-argon ages are preserved in impact-type rocks. And they argued that the impacts may have played a minimal role in terrestrial habitability, early Earth dynamics, and the formation of Hadean zircons. Their point here was that this late heavy bombardment, based just purely on argon-argon age dating, may not have occurred at all. The other obvious consequence of this is if you have an impactite, it's easy to preserve older ages, but it's not particularly easy to preserve young ages. If that impactite hasn't seen that event, you're simply not going to observe it. Michael et al. In 2018, they produced a very nice paper where they looked at and summarized all the available ages at that time for the Apollo and lunar missions. Of course, we now have more data from Chunga 5, which we could add into this, which would be great. But they concluded that from the statistics of sample ages alone, they contradict the terminal cataclysm scenario. And that's simply because if you look at these ages, what I've done is I've drawn bars at around 3.9 billion years. You can see there's this whole swath of ages that go to much older ages than this 3.9 late heavy bombardment. And they argued that this was possibly the effect of just the last stages of impact that occurred on the moon, rather than it being a significant cataclysm. They also observed evidence for the formation of impact basins that extended well beyond 3.9 to as old as 4.3. And this is, of course, incompatible with a short interval cataclysm. They were also able to show by models that impact ejector blankets allow the possibility of reworking. So you can have older impactor ejector blankets that are reworked by younger ones, as shown in this diagrams here. They pointed out that if we don't know the ages of these major basins that well, we could have 3 n-member scenarios. If, for example, the oldest basin, South Pole Aitken, which is the largest basin on the moon, is say 400 or 500 million years older than Oriental or Imbrium, then we would have an impact of crater frequency that would look something like this left-hand diagram, which would show a monotonically declining flux of impactors and crater formation. Whereas if we have a much more tightly spaced ages for these basins, we would have a late heavy bombardment. The key here is that we need to know which impactors come from which basins and what ages they are preserving. This is the key problem. One way of going about this, and it's somewhat loosely related to the location of the basins, is the type of impactor striking the basins. The way that this has been done for the last 50 years is to use highly siderophile elements. These are elements that prefer to be a metal over silicate, and they include osmium, iridium, ruthenium, platinum, palladium, and so on. The reason that these elements are so powerful is that in the moon's crust and in its mantle, they're in extremely low abundances. They have been sequestered into either a small lunar core or during the formation of the moon from the metal that was involved in the impact, presumably being sequestered into the terrestrial core. This means that you have essentially a blank canvas where the moon has no HSEs, no highly siderophile elements, and any impactors that are rich in these highly siderophile elements then leave an indelible imprint on that canvas of what they were and what type of meteorite or asteroid material they were. This has been known for 50 years. These are just 3 classic examples of these papers that have been used. From these early works, they suggested a whole variety of impactor compositions from different types of chondrite, so different types of early solar system product, to differentiated materials, including iron meteorites. The idea is shown here or portrayed in this diagram, where you have a highly siderophile element rich impactor striking the moon, which is a highly siderophile element core target. It splays out material, either in the form of ejector blanket material or impact melt that is intruded into the crust and mantle of the moon. And from this, you can determine impact composition. This is just a simple diagram of osmium, picograms per gram, versus the osmium isotopic composition. And this is actually real data from the moon. And what these models are showing is that if you have, very low contents of osmium in this particular case in the moon that are very radiogenic relative to the impactor materials, then you can very easily calculate the percentage of impactor material that's been added. And if you know the composition of those impactors, you can begin to tease out what they might have been. More modern studies from those 1970s studies have taken advantage of the amazing improvements we've seen in mass spectrometry, ionization efficiencies, and so forth, to produce a new generation of papers examining impactors striking in the moon. This is arguably the first paper in 2002 by Mark Norman, where they reported most of the highly siderophile elements, but not osmium and osmium isotopes, in poikilotic impact melts from the Apollo 17 site. Excuse me. They associated these melts with the 3.9 billion year Serenitatis impact event, on which the Apollo 17 site is closely associated. And they showed that most of their samples in space like this, platinum, palladium versus rhenium, iridium, normalized to chondrite. So chondrite would be here, this is CI chondrite right here, showed compositions that were closely affiliated to high iron enstatite like chondrites, EH chondrites. They had one strain sample in their suite that didn't look like that. It looked like it might have come from an ordinary chondrite or from a low iron type enstatite body. This suggests that materials in this particular instance were not strongly reworked. So if we go back to the Michael et al. Study, it didn't suggest there was a lot of reworking. And potentially, they argued, it was very strong support for a late heavy bombardment based on the age 3.9 and the consistency in composition of the impactor at the Serenitatis site. They analyzed a suite of quite complex rocks. These are just some images for you. These are in plane polarized light showing these different materials from the Apollo 17 site. Fielded views are shown here at 3 millimeters, 1.4 millimeters. These are in different types of cross-polarized, plane polarized, and reflected light, just to give you a sense of the complexity of these materials. And they noted that these materials were, this is what the definition of poikilotic is, smaller crystals enclosed within larger ones. They noted the predominant class of Apollo 17 impact melt rocks, which have poikilotic textures, relatively mafic compositions. And they pointed out that they have very creepy, incompatible element rich signatures, creep standing for potassium, rare earth element phosphorus. In modern equivalent, we would call it incompatible element rich. And you can see that very clearly here. This is the average lunar crust on a sample versus CI chondrites, showing various elements. And you can see that these Apollo 17 poikilotic rocks are incompatible element rich relative to the lunar crust itself. Since Norman, there have been a series of studies looking at measuring fragments of impactites from various parts of the Apollo missions. I'm sure that there are plans afoot to measure Chungo 5 samples as well, which will be very interesting. If you were to say in a sort of single sentence what these show, they suggest dominantly two component mixtures of a low H2C target and a high H2C rich exogenous component. And they have different flavors. They come from different types of impactor. The methods used by these studies shown here, showing their different locations where they were measured, are mainly, state-of-the-art isotope dilution, highly siderophile element studies of these rocks. So really robust data. Just to highlight some of these studies, one of the highlights was Fisher, Gerd, and Becker in 2012, who actually got an isochron, or an apparent isochron, for one of their impactites that suggested a very old age of about 4.2 plus or minus 0.1 billion years. Clearly not consistent with late heavy bombardment, and suggesting an iron meteorite-like impactor at the Apollo 16 site in this particular sample. They pointed out that later impacts were occurring on top of older impact signatures, confirming that there must be some kind of mixing going on during these impact events. Very complicated scenarios. Sharp et al. In 2014 suggested that both aphanites, so these are rocks that don't have this poikilotic texture at the Apollo 17 site, was similar to the poikilotic Apollo 17 rocks. And they pointed out that the dominant signature from these impactors could either come from things that weren't currently sampled in the meteorites groups today. In other words, the meteorites today, the chondrites that we find today, are not really representative of what the early solar system looked like at all. And all the material that was originally in the solar system has been swept into the planets. Or they argued that it could be an average mixture of two or more impactor compositions. Again, reconfirming this idea that maybe we have mixing going on, different impactors, different events. The key point about this is that all of these HSE studies looking at the impactors have not really looked at the lithology of the country rocks that they were striking. Only the Norman et al. Paper in 2002 really did this by measuring major and trace elements in their rocks as well as highly siderophile elements. And the point of the Sharp et al. Paper and others since then is that there could be significant major element heterogeneity in the impact melts themselves, coming from the country rocks, if you will, the crustal rocks of the moon that were impeding and changing the signature. Liu et al. In 2015, they looked at Apollo 15 samples from Imbrium. They supported the earlier suppositions of Fischer, Gödel, and Becker, and really showed Gleisner and Becker fractionation taking place within the impactors themselves that we need to take account for. And they observed partial melting of volatilization. The point is here that, we got this wealth of data, we have this wealth of information, but we need to tie together much better where the impactors are coming from, the lithological variations, and the ages to really constrain whether something like a late terminal cataclysm occurred. As I mentioned, the textures and other features of these rocks are immeasurably diverse. They range from fragmental breccias like this one, 67016, to fully melted and recrystallized rocks like 65055 over here. This complicates things as well when you're comparing these different types of rock, where you have clearly older class populations within younger matrix, and then you have these fully recrystallized rocks. What are you comparing, and how do you compare them? I think a fundamental paper is this 1994 paper by Randy Korotev. He used neutron activation analysis, and he took little tiny fragments from the Apollo 16 site, which is a wonderful site because it has this amazing geology that's been preserved on it, to look across the site at all of the locations that were sampled. So shown here is the distance in kilometers. This is looking north on the moon. This is showing you the Descartes formation. There's these diagonal lines, and then the Cayley Plains formation as this shaded region, and showing you all the sampling sites from the lunar module. So you can see that they went down to Stone Mountain and all the way up to North Ray Crater. He was able to analyze all these materials, and he noticed some fundamental variations. So the first thing is that he noticed is that the high scandium, high samarium, and high MgO group 1 and group 2 rocks, or rocklets that he measured, all came from this region of the Cayley Plains. He noticed that the low scandium, low samarium, low MgO groups came from this part close to the Descartes formation. This raises the important point of not just impactor variations, but also lithological variations existing even at a single Apollo site. And you can see these variations really nicely on these diagrams. This is from Randy's work. This is scandium versus samarium. You can see the very clear groupings. I've shown them here in the green and the red, so you can see the distinction between these group 4, group 3 rocks and these group 1, group 2 rocks. The problem is most people don't measure highly siderophile elements on the same aliquots that they measure trace elements on. And so you don't get this breadth of information that is so necessary to pull apart and tease apart what's going on in these impactites and what they're telling us about impact processes on the moon. And so you can kind of think about it this way. We have a tying between chronological information from crater counting and from argon, so forth, with lithological diversity on the lunar surface and the compositions of the impactors themselves. These three things provide us with the depth of knowledge that we would require to be able to begin to understand if a terminal cataclysm was possible or not. So now I'm going to switch gears and talk a little bit about some new data from the Apollo 14, the Apollo 16 site. I haven't put Chang'e 5 on here, but it would be just up here. So it's just to the west, northwest, I guess, of Imbrium. What I've shown are the relative ages of the major basins that you can see on the surface of the moon here. So Imbrium being the youngest, followed by Serenitatis, followed by Chrysium, Pomorum, Nectaris, Nubium, Tranquillitatis, and Faguntitatis. These are all potential sources of impact materials that you find at all of these Apollo sites. And indeed, I mean, if Chang'e 5 wasn't on young material, it would be also possible there too. The point is I'm going to be talking about two sites that are clearly in impact-rich material. So the first, the Apollo 14 site, which is in the Frau Maurer formation shown here, which is clearly a very important impact formation. And then the Apollo 16 site, which is on the Highlands and has been a witness plate for impact processes on the moon for at least 4.3 billion years. Starting with the Apollo 14 site, what I did was analyze creepy, so incompatible, trace element rich, supposedly basaltic rocks, but they're essentially impacts that have completely melted and recrystallized. This has the advantage that you don't have older class within younger matrix. It does raise the possibility that you could have melted older material into these recrystallized rocks. They come from all through the Apollo 14 sites. This is the Apollo 14 site. The astronauts made their way. You can just about make out the imprints here on the LRO data. This is an LRO image going up to Cone Crater, where they collected two Mare basalts. Actually, these are pristine Mare basalts that I've reanalyzed. They are definitely pristine. They don't look like impact melt compositions. But then I've measured these impact melt compositions over here. They're very well dated because argon, it's possible to do very precise chronology on these types of impact rocks at between 3.78 and 3.88 billion years, with a mean age of 3.84. At the Apollo 16 site, I analyzed impact rocks that are completely recrystallized as well. They've been known as Hyland Basalts. They're high alumina. They're in fact completely molten impactites. This is the textures that you would see. The scale bar here is 1 millimeter. This is showing you the Apollo 16 site. And they range in age. So some of them range between about 3.76 to 3.87 billion years, and others range to slightly older ages. The Apollo 16 site, we have these low MgO, group 3 and 4, and these high MgO, group 1 and 2 rocks. The high MgO rocks, the high magnesium rocks, are from the Cayley Plains, shown here. So this is Cayley Plains, this is Descartes Formation, mapped here by Billums. And this is just showing you a blow up of those spaces. So you can see North Ray crater is about here. And you can see that these other craters are just about here. So this is showing you blown up region. And this gives us an opportunity to look at both these groups and to understand what they're representing in terms of impact material. I measured the highly acidophile element data in these rocks, and I'm comparing them here with previously published data. So for the Apollo 14 site, there's 2 previously published data. One is for 14310, which I also analyzed. This is a plot of HSEs, highly acidophile elements, as a function of their sort of condensation temperatures, so going from highly refractory on the left to less refractory on the right. And their sample times 1000 over CI chondrite. So these are not enormously rich in HSEs, but they are quite rich in HSEs because they have impact material within them. You can see the data for 14310 that I've obtained is not too far off the data obtained by Fischer-Gerd and Becker. In 2012, they didn't measure osmium and rhenium in that particular sample. I did. They look pretty consistent. They look very distinct from 14321. This is a really interesting, very complex impactite. It's essentially a fragmental breccia. It contains bits of felsite, it contains gabbros, all sorts of stuff, very distinct. But you can see that the rocks that I've analyzed are quite consistent in their compositions. At the Apollo 16 site, we see much more variable and lower HSE abundances for the high MgO versus the low MgO impact belts. They're generally consistent with prior data from Fischer-Gerd and Becker, Liu et al., and so on. And you can see that I've split them into high magnesium and low magnesium. So high magnesium means Caine plains, low magnesium means Descartes formation for the most part. And you can see that there is some distinction. In general, these low MgO rocks from the Descartes, which is older, tend to be more HSE rich. We can also do all the things that have been done in previous studies. We can look at the composition of the potential impactors striking to form these deposits. One of the things that's really key here is look at the osmium versus, say, palladium iridium. You can see significant differences between the low MgO Apollo 16 rocks and the high MgO Apollo 16 rocks. There's significant osmium isotopic variability between these different types. You can see that the creepy Apollo 14 rocks that I've analyzed lie somewhere in between. And you can play different games depending on the type of impactor composition. You can tie these in to say that they have certain impactor types. And based on this, the high MgO rocks, they have distinct radiogenic osmium, distinct ratios of elements. So for example, ruthenium iridium, and they suggest a differentiated impactor similar potentially to some other locations and sites that have been proposed. The low MgO rocks from the Apollo 16 site, these have chondritic osmium, shown here, and they seem to be coming from an ensitite chondrite type source. The Apollo 14 creepy or incompatible trace element rich rocks, these are less radiogenic than the Apollo 16 high MgO or Apollo 17, and they suggest a possibly distinct ensitite type chondrite source. And as we mentioned before, the Apollo 17 site, it's thought that these are ensitite chondrites, but suggested to be outside the range by Sharp. This suggests that we have multiple types of impactors striking the moon. So if during a late heavy bombardment, if a late heavy bombardment was feasible, then this was not one singular type of impactor. This was multiple impactors striking the moon at that time. I measured the major and trace elements in all these rocks. So in the same aliquots. This is very important because now you can link the crustal lithologies that are being struck by these impactors with the impactor compositions and the ages. The Apollo 14 site is distinct in terms of the Apollo 16 site. You can see that really clearly here on this MgO versus phosphorus diagram. These creepy rocks are unsurprisingly rich in phosphorus. They have moderate MgO, around 8%. And compared to the high MgO rocks, the Apollo 16 site, some of the poikilotic rocks from Apollo 17, and so on, they're significantly less mafic. They look very similar to some of the materials that were found at the Apollo 16 site by Randy Korotev that are labeled here as 1N and 1F. You can do this for a whole range of trace elements. You can do it for lanthanum and lutetium. You can do it for a variety of things. And you can see these clusters of data. And in a nutshell, at least 5 or possibly 6 highly distinct populations exist in the data that we have so far. There could be more. And this suggests not just diversity in impactors striking the moon, but diversity in the materials that were being struck. So this suggests, these are not necessarily potentially coming from a single impactor location. So very important. And I've just shown the groupings here. So you can see these general groupings and clusterings of data. The levels of incompatible trace element enrichment in these rocks varies by quite a significant degree as well. So for example, the high MgO Apollo 16 rocks are not the same as the Apollo 14 creepy or Apollo 17 poikilotic rocks. And you can see that in these diagrams here. I now have an extended incompatible trace element diagram sample over CI chondrite. I now have all of Mark Norman's data here in red, and all of my new data shown here in the various symbols. You can see there's a big variety going on here, a lot of detail that I'm not going to get into, but you can see now how the groups relate to one another on these types of diagrams. The observation that Randy Korotev had of scandium, samarium, he was able to measure these by neutron activation very, very well. I can now plot my data on these diagrams, and you can see good consistency and coherency between what he found. In my case, I'm able to actually say what types of impactors potentially are forming these different impacted populations. So we now have an advantage. At the Apollo 16 site, there are at least 2 major ejector types distinguished by group 1 and 2 and by group 3 and 4. These are the Cayley planes, Descartes formation. They're telling us something very important about the mechanisms of how these impactites were placed on the surface of the moon. This is my sort of diagram. So Chunga 5 is just up here somewhere. This is just showing you on this near side image that I've manipulated a little bit. This is just showing you the very high uranium thorium area measured by gamma ray spectrometry. And then these sort of more marginally uranium thorium rich creepy regions. This is the Procellarum creep terrain that was defined by many others, including Brad Jolliffe. And now you can see what the relationship is between that creepy terrain, these different impact locations, and these sites. And what I'm showing here is I'm showing that the Apollo 14 site, which is right here in the creepy region, unsurprisingly has this very incompatible trace element enriched signature shown here by these rare earth elements. It's showing that the material from the Apollo 17 site, which is far from the creep region, has quite elevated creepy signatures. And at the Apollo 16 site, we have this diversity of material, not just creepy material or moderately creepy material, but also fairly incompatible trace element poor material. If we compare the ratio plots like these, we can begin to see similar trends. We're seeing evidence then that there are distinctive compositions at different landing sites. There's distinctive impactor populations at different landing sites. And we can begin to distinguish and tease out what these compositions might be. From this, we can say that the implications are that the Apollo 14 creepy rocks, these come from a distinct source around 3.84 billion years ago with a distinct ensitite chondrite-like impactor composition. The Apollo 16 low MgO rocks, these are reworked of 3.83 billion years ago. They might be partially coming from the older Descartes formation, and they suggest an ensitite chondrite-like impactor. At the Apollo 16 site, in the high MgO rocks, we slay a slightly creepy source associated with the Cayley Plains formation and a differentiated impactor, very distinct impactor. And at the Apollo 17 site, we see a creepy poikilotic rocks, 3.9 billion years or so, and a distinct radiogenic impact composition. What's the likely provenance of all these? How do we tie all this together? Well, this is just my initial thoughts. So by no means are they strictly, paradigm setters here. But I would guess that if I were to look at this and say, where does this creepy signature come from in the Apollo 14 site? I would guess that at 3.84, it's very close to the Imbrium event. And this makes sense because Imbrium is right in the creep terrain. So this is probably creepy Imbrium ejecta. For the Apollo 16 low MgO rocks, these are reworked, and this could be coming from Nectaris, far from the creep terrain. Distinct impactor, remember, very distinct from Imbrium. And the Apollo 16 site, where the high MgO rocks occur, this could be from Serenitatis. It could be from Imbrium if the Imbrium impactor produced a multiple layered deposit. The big difficulty is, of course, that those high MgO rocks appear to have come from a differentiated impact. And that would then suggest that they must come from a distinct source. And then at the Apollo 17 site, I would follow the current literature, but these are probably Serenitatis materials. Different ages, different potential sites, different impactors striking the moon. What does this mean for the late heavy bombardment? It suggests that the impacts that we're observing at these different sites were excavated over a very short period of time. They appear to require different lithologies. Now that could be, if they all have the same impactor composition, it could be from excavation of a deep impact into the moon's surface. So you impact deeper and deeper into the crust and you get different compositions. So for example, at the Apollo 16 site, you might argue that the Descartes formation type rocks with low MgO are coming from upper surface materials and the high MgO rocks coming from more like troctolites and deeper crustal materials. Problem is the impactor looks very distinct. It's hard to account for this heterogeneity of ejector materials and impactors in a single event. It seems to be distinct events. And this rapid succession of impacts means that you cannot discount a late heavy bombardment to the inner solar system planets. And so my favorite model at this point, and I'd be happy to take questions and talk with you about this, is that maybe we have something intermediate between these two extremes given by Michael. We don't have this relationship. Maybe we have something more like this. And until, frankly, we've dated South Pole Aitken and Oriental, we're going to have a hard time distinguishing between these events. And so that's the end of my talk. Thank you very much for listening. I'd like to acknowledge my collaboration with Clive Neal on this. I'd like to acknowledge Randy Korotev for his generous donation and provision of his database, so I was able to compare my data. And I'd like to acknowledge NASA for supporting me and my students and various other people in our continuing work. Thank you very much.
Okay, thank you, James, for your talk. And now it's the time for questions from our participants. So feel free to open your mic to ask a question, or you could leave your question in the chat and I'm going to read it for you.
So I would like to ask one question. Zhengzhou?
Please.
Yes,
Yeah.
please go ahead. Chunhui,
Yeah.
please go ahead.
Yeah. A very nice talk, James. And I have one question. If the late heavy bombardment is one of the process, let's say, related to the NIS model, which the NIS model brought a lot of stuff from the outer system to the inner solar system. And then the HSE in the Earth's metal could be related to the let's say to the ground tech theory or NIS model. Then we cannot distinguish late veneer and the late heavy bombardment. But if we go to the older rocks, let's say the 3.8 gigayears metal rocks from Greenland, those rocks all already had HSE abundance comparable to the modern metal. So my question is, if the late veneer and the late heavy bombardment are the same process with different names or with different definitions, characterized from different sides with evidence.
Yeah, that's a great question. How do I pronounce your name? Is it Chunhui?
Chunhui, yeah.
Chunhui. That's
Yeah.
an excellent question. I mean, this is a very important question, and I'm not sure that my answer is going to be particularly satisfactory to you. Is the late heavy bombardment the same as late accretion to the Earth? This is not a question that we have addressed fully. There are some people who would argue that yes, it is, and there would be some people who would argue no, it's not. But I would argue that the data is simply not sufficient. There's a couple of reasons I would make that argument. The first reason is based on the moon itself. If we look at these impactors striking the moon, they are not carbonaceous. They are not outer solar system materials. They are NCC. They're non-carbonaceous chondrite type materials for the most part. The second part of the moon argument is if you look at the moon itself and you look at the interior of the moon based on Mare basalts, so far as we understand it to date, it appears that the moon itself saw some degree of late accretion. Not much, but some. So that would suggest that this late accretion must have occurred somewhat early, because you set the sources of the Mare basalts at around 4.3, 4.2 billion years. The other part of this argument falls in place regarding the Earth itself. So on the first instance, those rocks from Greenland, those ones that are thought to be mantle rocks, very recently it was just shown by Pedro Waterton and others that these are almost certainly cumulate rocks. They're not mantle rocks. So this throws a bit of a wrench into the works, because it then suggests that potentially these signatures may not be truly mantle signatures after all. And then finally, of course, we have this evidence from komatiites that there may be a slow increase in HSEs with time. This is disputed. So I think on balance, all of this data combined together leads to very poor certainty about whether late accretion and late heavy bombardment are truly related at all. I would argue, based on the evidence, that the late heavy bombardment is not late accretion. It's part of it. It's the end point of it, if it existed at all. Late accretion is purely post-core formation accretion. So the moment you form the core and you broadly isolate it from the mantle, that's the point at which you can begin to accumulate siderophile elements into the mantle of whatever body you're interested in. Clearly, if you have large enough impact events, you can reset the system, because if they're large enough, you'll equilibrate the core with the impactor and everything else in between. So this is a very interesting problem. It's a great question. I'm sorry I cannot answer it definitively, but that would be my answer, is that we simply don't have sufficient knowledge to know what the relationship is.
Yeah, thanks very much. I also have another question. I mean, if we check the definitions of late heavy bombardment or Lithuania, let's say late heavy bombardment is defined by the ages of the impact rocks returned from Apollo, and the Lithuania is defined by the HSE abundance in the Earth's rocks. In fact, those are two different types of, let's say, process, let's say, artificial process. My question is that, I mean, there are also some other studies suggest that there is no such a, let's say, an intense peak at 3.8 giga-years. So I don't know whether we can define such a event by measuring the element abundance of the, let's say, fragments or not.
We can't. You have to. That's really the essence of this talk, is that you need all of this information, right? So you need ages, you need the impactor compositions, so you can begin to distinguish whether they were discrete events or not. And you need the lithological variations that are inherent in the impactites themselves. It's those three bits of information that give us any kind of confirmation of heterogeneity or homogeneity. This is possible on the moon because we still have those impactites. It's also very difficult, of course, Shunhui, because we don't have that great fieldwork information. You know, for example, at the Apollo 14 site, they didn't, if you actually read some of the rocks, they weren't even sure where they collected them from. They were not very well recorded. So we have that issue. And on the Earth, of course, we have the issue that none of this material is remaining anymore. So you need the ages, you need the impact compositions, and you need the lithological information to be able to begin to tease out the relationships between these discrete impact events.
Okay, thanks for your answer. Thanks very much.
Pleasure.
A great talk.
Thank you.
Okay, that's Shunhui from Chengdu University of Technology. So next question, please.
Yeah, Zhang Zhou. I would like to ask a question. I'm Yigang Xu.
Nice to meet you, Yigang.
Yeah,
Yeah,
Yigang,
nice to meet
please.
you, friends. Very great talk. I'd like to, would you please add some more how to distinguish from the petrological viewpoint the true mark volcanic rocks from those you said it's recrystallized impact melts? I think it's a very interesting point to start with.
Yeah, I mean, so in the first instance, if you can see my screen still, one of the things that we've been doing, I don't really talk about you're talking about the Apollo 14072 and Apollo 14053, I think. In the first instance, of course, you can measure the HSEs in these rocks, and they're extremely low in these two particular rocks. But you can also measure the textural variations in these rocks. This is a plot of crystal size distribution against iridium content for these particular rocks. And you can see that, you know, this is the trend, this red line is the trend for impact rocks. And you can clearly see these two rocks fall way off this trend. And they also fall off the trends in sort of MgO, magnesium versus iridium space as well. So I haven't dealt with these in great detail, but we're able to distinguish impact rocks from pristine endogenous rocks very, very well now using these methods.
Okay. So from these sidereal field elements, I agree, it's very clearly. But from the petrographic observation, does that make sense to the two different kind of rock can be distinguished under microscope on the, I mean, you use the naked eyes, you can make a distinguish between two kind of rocks.
You know, that's a great question. I mean, I would like to think when I see a rock, I can tell the difference between an impact rock and an igneously derived rock. But you're right. I mean, it's not that easy in all cases. It's this kind of quantitative textural analysis that can give you some insight into this. So Clive, Neil, and I have been collaborating on this issue because we're acutely aware that, for example, for Chungo 5, where you have very small rocklets, and you want to be able to define whether they're endogenous or exogenously derived, is there a method for doing this? And we would argue that actually doing textural analysis on these rocks is the first thing you should do, because it can give you really key insight into whether these are mare rocks or whether they are impact rocks. And so, you know, can you do it qualitatively by eye? Yeah, you might have a 90% success rate, but there's going to be some degree of uncertainty in that. Whereas by doing it in this sort of quantitative way gives you some confidence. And I'm not showing you all the data, but we have very strong correlations now between impact rocks, HSE contents, which are really a good indicator of impact, and so forth. So I think that would be my answer: is do quantitative textural analysis on these rocks. It's not hard to do. It's fairly straightforward, and it's I think very powerful.
Thank you.
Okay, next question, please. That's Yigang Xu from Hangzhou Institute of Geochemistry, Chinese Academy of Sciences. So.
Hi, James. This is Jinggao. Hello.
Hey, Jinggao, how are you?
Good. Haven't seen you for a while.
We're old friends.
Yeah, academic brothers, you know. Yeah, I have a question. You know, it was lucky for me to do some work on Apollo samples, but I haven't got a chance to do that since then, so it was a pity. I have a question about the composition of silver elements. For a sizable like impact, for example, Imbrium, like how can we have a homogeneous composition? I mean, is that possible during the impacting process? Then it fractionate composition. So that's why we see a continuously composition change in terms of the Hyland stuff and, for example, the ratios, as what we see in the rocks.
I mean, so you're asking, can it fractionate during the process? The answer is it could. This is certainly something that I've thought about quite a bit. In fact, in our sort of hidden away in our reviews in mineralogy paper, I actually did some modeling to show that this could indeed be the case. And so the answer is it's possible. The difficulty comes when the HSE signatures that you're observing are discrete and distinct. They don't follow trend lines. And this causes, of course, problems, because you then have to do some special pleading to explain it through some kind of fractionation. The other issue that comes up, Jinggao, is that inevitably, if you have high magnesium rocks and low magnesium rocks with these discrete osmioisotopic compositions that have very high HSE abundances, how do you do that as well? And so, it could be fractionation processes. It could be mixing of materials. However, to do this in all the sites, for example, this n-member model that Imbrium is the cause of everything, right? This is one n-member model. It's very hard to explain it in that way. You need at least possibly 4, possibly 6 discrete events based on the data we have. You might be able to collapse that down to maybe 4 events if you were to come up with some fractionation models, but I've been unable to collapse it down to 1 event or 2 events using that kind of method. So yeah, I think it's a possibility that some of the variation is as you described it, but I just
what about before the event, like for a sizable impactor, like but possibly the core is fractionated, right? Then during the impacting process, it's not going to homogenize that. Like probably different parts go into different impacting melts. Then we see different composition, the variability. Is that possible or what?
It is possible. Again, I've thought about this. If you have sort of a differentiated body, of course, it's a discrete size, isn't it? Because we know the size of Imbrium, we know the size of South Pole Lake,
Yeah.
we know these. So it's a discrete size. We're working with a finite mass. And so we would, you could make these arguments. You could say, okay, well, let's go with something differentiated to have a core that is HSE rich by definition because it's partially differentiated or fully differentiated. A silicate mantle that's HSE poor, unless it's somehow changed. So this doesn't change the problem, because even if you end up with an impactor striking, let's say, Imbrium that is differentiated, and the core of it goes deeper into Imbrium, and you say, okay, that explains why you have these tropholytic compositions, radiogenic HSEs, whatever. The problem is the rest of it is HSE devoid. And so you're not going to see it very clearly in the signatures. So this is why differentiated impactors are not particularly useful for describing this problem, because they, by definition, the HSEs are all in the core of these differentiated bodies, unless there's some other process that we're unaware of that's distinguishing them. So that would be my answer to that problem.
Okay, thanks. What's the other question will be, like, always think about this. What's the further implication of constraining the composition of the impactors, particularly for the late heavy bombardments? Can we have, because we always look at the moon, but shining on the Earth, right? So what's the implication for the Earth-Moon evolution system? Like, can we find evidence on the Earth for this process, like late heavy bombardment? It could be much bigger, right?
Yeah, so I sort of identified two parts to your question there. So the first part, what does it tell us about the late heavy bombardment to the Earth? One of the key things is that, none of these impactors look like carbonaceous chondrites, do they? I mean, very few look like this. They look more like ensotites or differentiated bodies. This is very interesting because that is not a prediction of some of these models. The second thing, can we see it in the Earth? Well, this is a bit harder because we know that we have very limited material that sort of fits in this age date. We do have rework material, don't we? We have, for example, at Barberton, you get these Hadean zircons, and these are in spheral beds at about 3.3 billion years. Maybe we can look at those and determine something, but I think it's a bit tenuous. I think, one approach is the approach that others have taken, which is looking at what they thought were mantle materials. If some of these materials turn out to be layered intrusions and things like this, then it does make the issue more complicated. I think another good witness plate is, of course, Mars. And, Mars is a really important witness plate in the sense that it's sitting well away from us. It's closer to Jupiter and Saturn. And, looking at materials from Mars, especially from the Perseverance rovers and as meteorites and so on, is also increasingly important in this work. But I mean, we're in the infancy of this, Xingao, you know this. And, this is a very exciting time to be in that sense. And I think Chang'e 5 could reveal some very important relationships, even though we're looking at predominantly younger material. And, so a very dissatisfying answer, but a truthful one, is that we really are, at the very edge of our knowledge right now.
Yeah, I may get a chance to analyze the Chang'e 5 samples, but just right now the sample amount is not granted yet. So I will try maybe later. Yeah.
I hope you do, and I'm looking forward to seeing the results.
Thank you.
Oh,
I will.
Go ahead.
Thank you, James. Nice to meet you.
Thanks, Xingyao.
Jingao's question is very good. Is very great. I mean, even if there is a, let's say, light heavy bombardment on the Earth, there is we don't have a kind of factor or parameter to distinguish it from other process. For example, we cannot use HSE, we cannot use osmium isotopes. I don't know whether this thinking is right or not.
In the sense of could you explain your question a little more clearly?
Yeah, I mean, even if there is really a little bombardment on the Earth at 3.8 giga a year, we cannot find. I mean, even if there is one, we cannot distinguish it from all other terrestrial igneous process. Can we?
Absolutely. I mean, you know, this is definitely the core of the problem, isn't it? Is that we're not able to make these arguments for the Earth. We can infer them, but the main witness plate that we have is the moon. And this was my point about Mars, because if we can go to Mars, which has seen more limited differentiation in the sense that it hasn't seen extensive tectonics, it's not seen extensive weathering, this may be another location where we see evidence for this. But for the moment, we're stuck with the moon. This is really the main witness plate for a supposed terminal cataclysm. And so we are left with very few options. And the point of, you know, what I'm presenting here is there a tactile way of being able to distinguish discrete events, distinct timings, and distinct impact compositions? And I would argue, based on the data I showed you, that there is. And I would argue, based on that you cannot discount a late heavy bombardment, but you notice I'm very careful not to say there was one. I'm saying you cannot discount. And this may require a lot more work, a lot more analyses. We need age dates on South Pole Aitken, we need age dates on Oriental, and we need robust age dates. We can't have inferred ages, which is one of the big problems, is that we were inferring ages of impact events because we thought we knew where these rocks were coming from. And, you know, this is not the case. So these are the important problems that we have.
Yeah, I just want to add a comment after Jim. The things for Earth, you know, if we say it's late heavy bombardment existed, but because during the preservation and also the impacting for the impact of the Earth system, because you know the impacting for the Earth was very minor, right? So we cannot find the very good evidence for that. That's why James said we look at Mars. Maybe they can have better preservation to show us about this process. That's what I think. Yeah.
If I were to have my way, I would look at Mercury, but we can't do that quite yet. So this may not get solved in our lifetimes, guys. This is the truth of the matter.
Okay.
So we can wait for the Marshall samples return, right? We'll see.
Indeed. I make an argument, actually. I made an argument last year. I haven't published it. That, you know, Jezero crater is actually a perfect target. And I made the argument that they should collect as much impact-related material as possible, because this material is coming off Nili Fossae, which is one of the oldest units on Mars, into Jezero Basin. So you're going to get this amalgamation of all sorts of stuff in the sedimentary fan that forms there. And if you can tease that apart, then you will get, you know, decent chronology on this material. And some of it's very olivine rich, I would point out. So, you know, we're looking potentially at mantle-derived materials.
Okay.
Hopefully.
Okay. I will ask a last question, I think, for today's webinar. So in your published work, James, that you argue against the idea proposed by Brennan of the regolith contamination. But if we only look at the mantle source of the moon, for lunar mantle source that produce this lunar magmas, that do you think that they are sulfide saturated or not?
Yeah, I mean, I knew you would ask me that question. You just pulling it out there for me, Jingao. So, sorry, Johnny, I was thinking about Jingao. So just so everyone knows, Jingao and I were at Maryland together, and Johnny and I were at Scripps together. So this is the link that we have. And Jingao and I spent many an hour in the lab together. Fondly remember that, Jingao. So this is showing you, on the right-hand side is from this paper where I argued against James Brennan's arguments. So are they sulfide saturated during their initiation? And James Brennan had a number of arguments, which I'm not going to go into too much detail on, but one of them was experimental. And the other was this idea that you have regolith contamination in the basaltic rocks. Now, I'm just going to focus on the regolith contamination because Johnny, you're far better equipped to tell me about his experiments. But one of the key features that we observe in these rocks, in these Mare basalts, so this is showing you all the data for Mare basalts, is that first off, they have a very restricted iridium contents. So you notice that there's this thing here of iridium versus MgO in the top left-hand corner, where you find no magmatically derived lunar basalts fall into the region above about, I think it's about 50 parts per trillion iridium. Now that is strange because that's not what you would predict from regolith contamination. And the reason is these basaltic rocks would need to know that they cannot assimilate anymore. This is a big problem, thermodynamically, and in terms of the impactor compositions or the material of the regolith that is being assimilated. So this is just a basic argument saying this is very difficult. The other thing is that when I redid Brennan's models and compared them with these different basaltic rocks from the different impacts, different Mare basalt sites. Sorry, my brain is on impacts at the moment. It's also a struggle to fit these models with these data. And so this was my main argument against Brennan. And I think one that he ignored in his Nature Science paper entirely, because all of this was self-evident when he produced this paper. So do I think that they're sulfide saturated? No, I do not. I don't think the evidence is there. And I need to be more strongly convinced that the evidence is there. That was the point of this paper. It's not to say that he's wrong, it's to say that it's very unconvincing.
Okay. Actually, from the experimental, I could add a comment on this, that from the experimental perspective, it's interesting too, because Brennan happened to present the experimental evidence that just at the, just at the oxygen fuel gas range, that this could possibly work out. I mean, it would necessarily mean it would work out on the moon, but it just could work out by theoretical forward modeling. Because if the oxygen fuel gas is slightly higher, like comes to the Earth's mantle conditions, then definitely it will be unsaturated. There's no doubt about that. Or if it becomes more reduced, like towards Mercury, then it's become undersaturated for sure. So it just happened to be in this middle zone that appropriate to Moon's condition. That there is a possibility that make it sulfur saturated, at least from forward modeling perspective. Okay, Chenghui, do you have final comment or final note to add before we some
No,
of
no,
this
I mean,
webinar.
you have asked my question just now.
Okay,
thank
great.
you.
Okay,
Thanks
great.
for these
Thank you
wonderful
very much.
questions, everyone. This is really wonderful. So
Yeah, it's great. We have James today, and sorry for keeping a little bit long than what we expect. So thanks everyone for your participation, and thanks James, Jay for your talk. And our webinar will occur again next week, next Wednesday morning at the Beijing time. So see you next week. See you, James.
may I just say, if you're interested in talking more, just feel free to email me. My email address, I think Johnny has it, so just get it from him, and happy to always talk to you guys and hear your thoughts.
Thanks. Bye bye.
Hi, James.
Bye-bye.
Can we talk a bit more
Sure.
afterwards? Yeah, after
Sure.
people dismissed. Yeah, I just want to say a little bit more about other things, not just about science, right? Because I haven't seen you for a
sure.
while.
I know.
Yeah,
Well,
yeah,
since you were here at Scripps, right?
Yeah, probably.
Yeah, by the way, sorry guys, because this room will be occupied 10 minutes later by another meeting. So
Yeah, that's okay. 5 minutes is enough.
yeah.
Can we say 5 minutes? Or
Yeah, sure. Until 10:30. So the meeting will occur at 10:30. So if you don't
Yeah,
mind, I
that's
will just leave it as it is now. Yeah.
okay.
Sounds good.
Thanks.